Okay, thank you for your introduction. I'd like to thank the organizer to have a nice such conference. And also it is my first time to visit India, and I'm very happy to talk here. Thank you. So today I'll talk about the resolution of singularities and the McKay correspondence. So it is a kind of bridge between geometry and algebra. So and I will introduce something. So normally I draw this kind of picture, so-called mind map, to give to prepare my talk. This is my content of my talk, but I'll start my talk from this part. Anyway, so first of all, I want to introduce myself and my institute. And I came from Japan and IPMU. So the name tag says IMPU, but it is IPMU. And it is the Institute for the Physics and Mathematics of the Universe. So it is our Institute for the Universe. So we are working for the universe, but I'm doing only mathematics, but some results are related with string theory. So many people are working on physics and mathematics and cosmology and astrophysics. And this is a picture of last October. And this institute is 15 years old. And there are many people here, and it's really difficult to see which one is which one, but the female percentage is very low, but it's similar to Japanese average. And in mathematics, maybe it's less than 10% female. And but this is a very special institute because it is in Japan, but our common language in the institute is English, and more than half people are not Japanese. So it's very international institute, and we have a tea time every day at 3 o'clock, and we meet together and discuss not only math and physics and also the severe cultures and so on. So it's very interesting place. So if you have a time to come to visit, so please come ask me, okay? So this is my introduction and also my institute. So today I want to introduce elementary algebraic geometry first. So the algebraic geometry says geometry, it is geometry, but algebraic, because we use algebraic equations and so on, so-called polynomial equation. And in general, we use the algebraic variety, and which was defined by several polynomial equations. But today, I only use one equation for one varieties. And in general, these Fi's are polynomials, and we consider the solution of these equations as a geometry. And we use a ring theory to consider a geometry. So then we call it algebraic geometry. And for example, this is the one example. So x cubed to y squared minus y squared equal to 0. So you can draw this graph. And this graph is, this part is a solution of this equation. Then this shape has a singularity here. And what is singularities? The definition of singularity is here. So if the point P on that variety is a singularity, then, so if it is defined by the f x, y equal to 0, then PQ should be a point on the P. And also this derivation became 0. Then point PQ is a singularity. So in this case, you can consider these equations, then only 0, 0 is the equation of this condition. Then this has only one singular point here, and it is a singularity, so it's called singularities. So, but the singular definition of singularity is this one, but in general, in normal life, it is easy to find non-singular space. So if you, maybe many of you know this toy, so-called beads coaster, and these beads can move around here, along to the wires. But if this wire is singular, then you cannot play with this. So maybe baby angry with this. But for example, if this point is just combined, then you cannot go up. So you cannot move these beads here. Then this can be a singular point. But this point and the other point is a different point. Then you can move these along the wires. Then this is non-singular example. So if these cannot move, then it is singular. So it is easy definition of singularity, I think. So if there is a singularity, so for example, in beads course, if you have a singularity, you cannot play with it. But in general, in algebraic geometry, we also have a singularity like this. Then it has also some problems. And then we consider smooth space in spite of this singular space, so-called singular resolution of singularities. But why do we need the singular resolution of singularities? Then when we classify the algebraic varieties, we need to classify several varieties. And some variety has singularities and some variety is smooth. But in general classification of algebraic variety, we need some rules, and for rules for singularities. So in dimension 2, the complex dimension 2, we have a smooth minimal model, so-called, we consider we have several varieties, but we need to consider the birational maps, and you can get some more smoother, more nicer models, so-called minimal models. And in dimension 2, we have all minimal model has no singularity. But in dimension 3, we have terminal singularities, and in higher dimension, we have also terminal singularities. So terminal is the end of the some birational maps, and we have terminal singularities in general for minimal models. Then we need to consider the resolution of singularities. So before that, just make a special singularity in dimension 2. So this is quotient singularity. So you can make many singularities by some action, but the group action is the easiest way to make singularities. So let's consider the finite subgroup of SA2C. So it can be written as a 2 by 2 matrices. And the quotient C2 over G has a singularities. And this singularity is very special because they have many names: rational double points, dual singularity, simple singularity, and canonical singularity. So the last one is singularity which has appeared in the classification of algebraic varieties. A simple singularity, the name of simple singularity relates with today's topics. And dual is, I don't know about the classification of the singularities, and the rational double point is a rational, so because rational and double points. So this is classified to 5 types, and this is also, all of them are given as a quotient by the finite subgroup of SL2C. So let's consider one example. So if G is this type, so it is the order 2 cyclic group. It's very simple, and it's just generated by minus 0, minus 1, 0, 0, minus 1. And let's consider the more ring theory a little bit, and G invariant ring. So G invariant ring is written as this CXY D, and the action of G is there are only one element, G and identity, and the G act on X to minus X and Y to Y minus Y. Then we should consider the invariant polynomial in this action. Then X squared goes to X squared, and Y squared goes to Y squared, and XY goes to XY. Then these are part of invariant polynomials in this space, but in this ring, but it is a generator of this all invariant monomials and polynomials. Then if you put X squared to large X and Y squared to large Y and XY to Z, then there is a relation between them. So if x squared times y squared equals to x y squares, then there is a relation xy minus d squared equal to 0. Then we can consider this quotient space as a spectrum of this ring, but it is easy to understand this space is defined by this defining equation in C3. So this is a R3 picture, but if you immerse in the C3 space, you have this singular, this plurality xy minus d squared equal to 0, and it has a singular point here, only one singular point. It is isolated and hypersurface singularity, and the name of the singularity called A1 singularities. So this one comes from the order, and the name A1 comes from 2 minus 1. So I will tell you the more general one, but in this case, we have only one point, and which was written as this one around the origin. Then this has singularity. So as I told you, we want to consider the resolution of singularities. And at this point, the definition of the resolution is something like that. It's very rough definition, but if you have a morphism, it's a birational morphism, and X is a quotient space, and Y is a resolution. And we have a point P as a singularity, and the point P should be smooth later in this whole space, but other place doesn't change. So the other place is isomorphic. Then this picture is very easy to understand the resolution of singularities. So here we have a singular point. So you can move around easily this part and this part, but you cannot move here. But after resolution, you can move around everywhere, and only different place, this and this, topologically different place is this one and this one. And this is isomorphic to the P1, so rational curve. So this picture is a little bit different from real algebraic geometry because it's a real algebraic geometry, but I consider a complex algebraic geometry. And this is the P1 is the so-called rational curve. Then I showed only one singular point of type A1, but AN singularity is given by n plus 1 cyclic singular groups action. Then the generator is epsilon 0 and 0 epsilon minus, epsilon n plus 1 is 1. Then we can consider the similarly the invariant ring, and after consider the invariant ring, you can get these equations. So this equation, last place here, I write down only xy minus d squared equal to 0. But after you taking the, if you change the coordinate, you can write down x squared plus y squared plus d squared equal 0. Then similarly, you can get this equation for this case in general. And this one is a defining equation of AN type singularities. And after the minimal resolution of these singularities, you can get some space, a special place like this. And in general, if you consider the AN case, so this part, so-called exceptional set, is a set of curves, n curves, and n rational curves, and each of them intersect only one point to other curves. Then you can draw the dual picture, dual graph of this exceptional set. Then so the curve goes to the vertex, and the intersection point goes to H. Then you can write down this diagram. And it is same as the thinking diagram of AN type. And please remember this situation, because I'll tell you a completely different story from next slide. So now we have a finite subgroup of SL2C first. So let's consider the group representation theory. So let's take rho I to irreducible representations up to isomorphism, and let's put rho 0 as a trivial representation. And also take rho natural is a natural representation in SL2C. So this is two-dimensional representation. And if you consider the tensor product, rho I tensor rho natural, then the rho I is a basis of the representation space. Then you can write down as a summations, linearly combination of with basis rho J, and you have a quotient AIJ. So this AIJ can be a integer, but and in this case, if you consider if you consider the G in SL2C, AIJ and is the same as AJI, so it's symmetric. And this symmetric, if you consider the symmetric matrix, and please forget the part corresponding to trivial representations. And this is n times n, and n is not trivial, but some. If you have the number of the irreducible representation k, then the E is a k minus 1 times k minus 1 times identity matrix, and it became a Cartan matrix. It is John McKay's observations. So it is just a result, but let's try consider. Then as I told you, there's the quotient AIJ, it's just an integer. And if it is not 0, then you can draw a picture from one vertex I and J and with one edge. So you can connect the two vertices by one edge. But if AIJ is 0, then there is no relationship between a vertex I and J. Then if you consider for every case, it's for every finite subgroup, which is cyclic, binary dihedral, and binary tetrahedral, binary octahedral, binary hexahedral, then the result of this tensor product and the relation with this vertex and edges, then you will get this kind of linking diagram, which so-called simply, which is related, correspond to the simply algebra with simple raised, and A and DN E6, E7, E8. Okay. Do you have any questions? Okay. So this is only group theory and representation theory side, and we have only finite subgroup here, GL2C, and we consider the tensor product of representations, and we got some numbers, and if you make some numbers, but this Cartan matrix also appear in the classification of simply algebra. Anyway, we can get simply algebra from finite subgroup of SL2C. So there's no relationship in general, the group, finite group and simply algebra. But McKay observed this phenomenon. So as I told you before, we have a similar diagram here. So this is a linking diagram AN time. And if you consider the resolution of singularity for any other quotient by G, G is a finite subgroup of SL2C, then the extension divisor has many rational curves, and the configuration of rational curves is similar to the AN, and also the dual graph of other groups is similar to the linking diagram of E and D and type, like this. So if you consider the resolution of singularity of binary dihedral quotient singularities, then the dual graph of the exception divisors can be a linking diagram Dn, and so on, so on. So this is very, very unnatural. It is a case-by-case computation, and it is non-natural explanation, but there is one phenomenon observed by John McKay. And other things, there are different computed by exceptional divisors by getting minimal resolutions. Then we have the following diagram. So we start from the quotient space, finite subgroup of SA2C. So if you consider the singularity, you have a minimal resolution. And they have exception divisors, so-called exception curves, which all of them are rational curves. And there is some configuration here. And the Dirac graph become a linking diagram. And on the other side, you have a reducible representations. And if you consider the tensor product, you can get some number Aij, and this gives a linking diagram. Then there is a rotation. By this construction, there is a bijection between the exceptional curves and non-trivial representations. So you have to forget the non-trivial representation to get this diagram. Anyway, there's a one-to-one correspondence between exceptional curves and reducible representations. It's a very, very strange phenomena, but very interesting. So why it happened and so on. So many people worked on this after that. And it is a finite subgroup of SA2C. And some people after that, so this was done, so the Algebraic geometry, John McKay found it in 1979. And after that, the Gonzalez, Pinberg, and Batyrev compute some algebraic stuffs, and they proves the existence of McKay correspondence. So this was called McKay correspondence. So there is a one-to-one correspondence between exception divisors and representations. But it was only for group or SA2C. So some other people try to consider for another groups. So for example, if G is in GL2C, then there is also the minimal resolution. But the number of exceptional curves is smaller than the number of non-trivial irreducible representations. But after that, after their works, so the Ellen Arnaud and also Bunram want there is some special representation here. And if you, I don't talk about the definition of speciality, but if you choose special representation, each special representation corresponds to each exceptional curves. So-called, it was called special McKay correspondence recently, but it is a generalization of this two-dimensional McKay correspondence. So, but it is a two-dimensional situation. So when I was a graduate student, I tried to consider the three-dimensional cases. But at that time, there's no known result about three-dimensional resolution and so on. So I tried to find the classification of finite subgroup of SA3C first, and I finally found some relation with a representation, not only the representation, but also with string theory. So it's not string theory, maybe I should say superstring theory. And in superstring theory around 1985, so it was a very, string theory is a very popular among physics, and also they considered the new things, so-called Obi-Hall-Euler characteristics. So it was defined as follows. So M is some space, smooth space, and G is a finite subgroup act on M, but M over G should be a Calabi-Yau because in superstring they believed, so I'm sorry, I say believe, the universe is 10 dimension and the time and space is 4 dimension. And there's a remaining 6 dimension space, and it is a compact Calabi-Yau space, they think. And then they computed something about Calabi-Yau varieties. So M over G, when M over G is a Calabi-Yau variety, then they considered the Obi-Hall-Euler characteristic. And it was given by as follows, that G is a finite subgroup, and this one is the order of group, and take a summation over every commutative pairs. H and G is the element of G. And this one is a little bit different, but this is a topological Euler number of H fixed point and G fixed point. So intersection of H fixed point and G fixed point here. Then this is a normal mathematics. And this is the normal mathematical computation, but they consider this number. And if you consider M is C3 and G is a finite subgroup of S is 3C, then by this equation, you can just easily get this number is just same as the number of conjugate class of G. So before I show you in dimension 2, there is a one-to-one correspondence, exception curves, and non-trivial representations. But in this situation, the topological Euler number of this space is just same as the number of rational curves plus 1. It's same as the number of irreducible representations. Then in this space here, in group theory, the number of conjugate class of G, if G is finite, then it's the same as the number of irreducible representations. So it was a kind of three-dimensional McKay correspondence if holds. Then it was proved by Markshevich and Rowan and myself. So there's a number, small number here, because we consider case by case using the classification of finite subgroup of SS3C. And you need to prove this theorem. You need to show 8 papers. But anyway, as a result, if G is a finite group of SS3C, there exists a Crepant resolution, which is a kind of minimal resolution. And if it is a like Crepant resolution, then that topological Euler number is a mathematical topological Euler number. It's just same as the conjugate class of G. Then the physicists tried to compute some numbers, but it was a number on topological Euler number of the mini Crepant resolution. But I met some physicists after proving this theorem, and they never considered the resolution, and also they never cared the existence of Crepant resolutions. They just compute some number here. But occasionally, it was just same as the topological Euler number of Crepant resolutions. And to compute some resolution of singularities, so after that, we compute something. And it's one example of representation, not representation, it's one example of resolution of singularities and also called Crepant resolution. So I didn't say in dimension 2, but in dimension 2, if we have a question singularities, or any case, if we have a singularities, the minimal resolution is unique up to isomorphism. But in dimension 3, we can take minimal resolution several types, and also called Crepant resolution. So if you have a one quotient space, you can get many Crepant resolutions in general. But we consider one special Crepant resolution, so-called G-Hilbert scheme. Maybe if you read some paper related with McKay correspondence, we will see a G-Hilbert scheme, and which gives a very good correspondence between representations. But it is not so clear like two-dimensional case at this moment also. And we consider the several pictures for this kind of research. So this is a three-dimensional case. So in three-dimensional case, so if you have G in SFCC, or Crepant and quotient singularity has canonical singularity, but not terminal, then we can get a Crepant resolution, so smooth minimal model in this case. And if it is true, then you can consider also more global version. So it is a local version, but if you consider the global space and the action on G, and if it is a Calabi-Yau space, then you can consider this number can give a Euler number of the resolutions. Then I want to show you one more things about the higher dimensional case. So there is a theorem by Batyrev, and he considers a higher dimensional case in general. But it's very difficult to find the resolution of Crepant resolution. Then if you assume the existence of Crepant resolution, then the topological Euler number of the Creplant resolution is same as the conjecture class of G. It's a very beautiful result, but there are some problems. So problem one is the existence of Creplant resolution. It is not known in general. And if you consider GL, SL, and K, here we consider only C over C, but if you consider the positive characteristic space, so this doesn't hold. So there are some specialty in SL case and also even in dimension 3. And some cases in dimension 3, even in dimension 4, we have some counterexample which has no Creplant resolution if it is in SL4C. And yeah, here. So, and after this theorem, Batyrev consider stringy orbifold Euler number and also some stringy topological invariant, because if you consider the G in the GL and C, so the number of the orbifold Euler number gives just the number of conjecture class of G, and if it, in general, it is different from topological Euler number of the resolutions. But if in it is number was defined for Calabi-Yau space in three-dimensional Calabi-Yau space in superstring theory, but it was generalized in mathematics as string orbifold and so on. So there is such kind of generalization I want to show you here, and this is my talk. Thank you. That I'm all. Thank you very much.